Hello, today I'll be going over the basics of a mathematical approach to linear regression. In linear regression, we have two variables with known values, x our input variable and y the output variable. For example, let's say we have the values 1, 2, 3, 4, and 3, 4, 8, 9. We can think about graphing the x, y values on a plot. It's going to look like and then we can draw the trend line or line of best fit, which is going to be the output of linear regression. It's the line that goes through the center of the data points, minimizes the square distance from each point to the line. So in this case, 1, 3, and 4, 9 are going to lie on the line, and then the other 2 points are slightly apart from the line, right? So it doesn't exactly fit a linear equation, but this um, linear equation is a pretty good fit. And since it's a linear equation, we have the form y equals mx plus b, where m is our slope. So that represents the change in y over the change in x. And then b is our intercept, which is the y-intercept, the point on the y-axis when x is 0, what is y, right? And these are going to become the unknown parameters of a linear regression model. And we're going to call them beta 0 and beta 1 instead of m and b, right? And then our x and y are random variables. They don't have to be these specific numbers, but they do obtain some specific numbers. It's not every possible x value. We have an observed data set, and we're fitting a line to it. So rewriting this, we have y equals beta 0 plus beta 1x. The b turns into beta 0, m turns into beta 1. We capitalize the x and y to denote their randomness, and we're not going to exactly follow on the line. Some of the points are not on the line. So we also have this EPS term, which represents the error or random noise uh, in the data set, right? And so we can also denote the notation for each row I. So if we were looking at row I equals 2, we have x is 2 and y is 4, right? So we're just going to add subscripts to show that like it's not our beta and beta 1 changing, it's our yx and eps changing. And then the key assumption in linear regression is about this eps, the error, the random noise in the model, how far the points are from a perfect line, right? We're saying that each epsi is a normal distribution with 0 sigma squared. So that means our expected value of epsi is 0, and the variance of epsi is sigma squared, and that's uniform over all I. The variance is not changing as we change which data points we're pulling from. It's like the order of the data points doesn't matter. It's a truly random sample, right? And so putting these together, that means our expected value of y given x equals x. So if we choose an x value, what's our expected value of y? That's going to be beta 0 plus beta 1 x plus the expected value of epsi, which becomes 0, right? So our prediction, we're predicting that the error, the random noise, is 0. And our prediction is just the output of the linear equation. And so we can call this y hat. So this is our prediction. For a given x value, we can get the predicted y hat. And then we're asking, well, in order to do that, we need to decide what beta 0, beta 1 were. Here, I showed you an example where it's intuitive what they are, but in the general case, we want, or even mathematically, we want to show that this line is the best fit, right? So we're going to choose beta 0, beta 1 according to minimizing a loss function. And the specific method we're going to use is least squares. So we often called LSE for least squares estimation, or OLS for ordinary least squares, right? And that's going to get us our estimates for beta 1 and beta 0. So generally, we could choose any beta 0, beta 1. We just wouldn't have a very good model. When we put the hat over it, that means we're choosing a specific value for beta 0 as the estimate for beta 0, right? And so, as I said, these are going to come from minimizing some function of beta 0 and beta 1. And in least squares, this function is sum of squared error. So we're taking each data point, squaring the error, and then adding them together, right? That's the same as, so this EI, EI is yi minus y hat I. So the difference between the true value and the predicted value that we said we're denoting with the hat, right? And that comes from this equation. So we can, let's plug those in here. It's the same as the summation over all the data points of yi minus y hat I squared. And then we can sub in our equation for linear regression, the prediction of y hat here. And so we want to minimize this quadratic function, find the extrema. Calculus 1, we learned we can find the first derivative, set it equal to 0. So dl d beta 0 is when we take the derivative with respect to beta 0, right? That's going to be negative 2 times this, since we have this squared up here and a negative sign there, times the summation yi minus beta 0 minus beta 1 xi. And then dl d beta 1 is pretty similar, except now we have that xi term that's also going to be multiplied using the chain rule. And then to find the optimal beta 0, beta 1, we want to set these equal to 0, and both of them at the same time, right? So let's write out these equations again and replace beta 0 and beta 1 with beta 0 hat and beta 1 hat. And then set it equal to 0. So this is just going very slow to denote the notation difference between beta 0 and beta I. Beta 0 hat is when we specifically done the least squares estimation, set the derivative equal to 0, and solve. And this might not seem easy to solve algebraically. In fact, we'll just skip that and go to the answer. But before we do that, there's some notation that will make expressing the answer a lot cleaner. So when we have x bar, which is the average of our sample x. So it's the sum of the data points divided by the number of points. Take each edge, add it up, and then divide by the number. And same for y bar, except it's the sample mean of the y's. And then we have SXX, which is going to be this sum from I equals 1 to n of xi minus x bar squared, right? That's like this one is the sample variance of x, right? just without the n/1, n-1. And this summation is equivalent to if we did sum of xi squared minus 1 over n sum of xi squared. And now I'm not writing the I equals 1 to n because we're just going to assume that's the case when I write the big sigma summation. And going off of that, we also have sxy, which instead of multiplying xi minus x bar twice, we're doing x once and y once. Sum xi minus x bar, yi minus y bar. And that's going to be the same as sum of xi yi minus 1 over n sum of xi sum of yi. And then syy is going to be sum of yi minus y bar squared. And how could we compute that faster? It's the same as this sxx, just replacing the y's with x, the x with y. And so given that, we can express this solution beta hat 0, beta 1 hat down here. So beta 1 hat equals sxy over sxx, right? So here, this thing divided by this thing, no, I'd underline the long ones, but anyways, just a ratio to those gives us the beta hat directly. Beta hat 0, after calculating beta hat 1, then we can calculate beta hat 0. It's going to be y bar minus beta hat 1 times x bar. And it doesn't really matter when y or x are undercase or capitalized. Some people write them all caps. Some people write them all lowercase. I kind of mixed them. Right? And so using these equations, that means we don't need the entire data set. We only need a few features of the data set. We need n equals some value. We need the sum of x. We need the sum of y. We need the sum of x squared, sum of y squared, and the sum of xi times yi, the dot product. Right? So we just need the two sums, the sum of squares, and the dot product, and then the number of data points. And that's all we need to plug in the calculations to find this beta hat 1, beta hat 0, and everything else that follows from that. Right? So think of doing an example without a calculator or with only a basic arithmetic calculator, knowing these points. Yeah, and then the other important notation, instead of using sxx, syy, so some people don't do that. The other important notation is the ANOVA table. We call that ANOVA for analysis of variance, because the start of the table gives us alternative notation to this, then it keeps going to give us some analysis of the linear regression, right? So we're going to say SSR is the sum of squares residual. Sum of squares, regression. Sum of squares regression. And that's the same as SXX. And SSE is the sum of squares error, which is our loss function, taking each error and squaring them. And then SST equals sum of squares total, and that's the same as SYY. And so doing it this way, we have SSR plus SSE equals SST. So an easier way to compute SSE than finding all the predictions and the differences between them, the faster way is doing SSE equals SST minus SSR equals SYT yy minus sxx, right? So as I said, it's a table. Let's start putting these in the tables. So we have the R for regression, E for error, and T for total. And then the SS column is going to be for the sum of squares, right? So the SSR we said above is SXX. SST is SYY, and SSE is SYY minus SXX. And then our next column is for the degrees of freedom, which corresponds to the statistical distribution that we're going to be drawing from in the ANOVA test, right? So this is going beyond, we could use these SSR, SSE, SST to calculate beta 1 hat, beta 0 hat, right? And we can also go beyond that to form an ANOVA table, right? So DF for R is always going to be 1. For E, it's always going to be n minus 2. So our number of data points minus 2. And then the total, again, is the sum. 1 plus n minus 2 equals n minus 1. And then our next column is the mean squares column. That means we're taking the sum of squares and dividing by the degrees of freedom for each row. So maybe we just write this as SSR divided by 1 and SSE divided by n minus 2. And then we don't have a mean squared total. That's not relevant to our test. The next column, we're only going to have a single value, and that represents the F0, the test statistic for the test, right? So that's going to be this value divided by this value, MSR divided by MSE. And let's go ahead and erase those circles. And so that this test statistic directly gives us the p-value, or we could compare this to some critical value, whatever. But if we were doing a p-value, we would take the F distribution with degrees of freedom 1 and n minus 2. So 1 comma n minus 2 of F0, and our F0 again is MSR over MSE, which we've shown can be directly calculated from these guys, which are directly calculated from these guys. And then this p-value is going to tell us whether the coefficient of the linear regression model is significant. And here, this is only beta 0, beta 1. If we wanted to add more betas, the ANOVA table would look a little longer because we'd have more rows. The other key metric besides the p-value from ANOVA to measure the strength of linear regression is the R-squared coefficient of determination. R-squared is going to be between 0 and 1, and closer to 1 is better. That means the line is a closer fit to the data, right? So by definition, our R-squared is 1 minus SSE over SST. The sum of squares error divided by sum of squares total. So it's like we take the ratio of how much error there is relative to the magnitude of the data and then subtract that from 1. Right? It sort of represents how well they are linearly correlated. And so this we can plug in our definitions, EI squared, like taking the error for each row, squaring it, and then our SST is same as SYY. And so that's 1 minus sum of yi minus y hat I squared. That's what our error is, the difference between actual and predicted. And then SYY, I keep saying that wrong, is yi minus y bar squared. So like the difference is the numerator we have the prediction, the denominator we have the mean. And then how would we actually compute this quickly in terms of these quantities I showed above? Well, let's do some simplification. So 1 minus SSE over SST equals 1 minus SST minus SSR over SST, using the property that, right, this thing here. And so that's 1 minus S. Oh, well, I mean, here, let's go ahead and just get rid of the 1 minus, right? So SST on top and bottom, that just leaves us with SSR over SST. And then we have SXX over SYY equals substituting in what those were. So this one is taking each x value and squaring it and then adding it together. This one is taking each x value, adding it together, getting the total sum, and then squaring that total sum. So it's both of them are always going to be positive, or 0, if in the very special case. Yeah, and so r squared close to 1 is a good thing for our model, and ANOVA with a good p-value is good. But we can also look at that core assumption directly, right? We were saying our core assumption is the variance of error, or our variance of the model, is given by EI as normal 0 sigma squared. So you could look over the I is the distribution of sigma squared relatively uniform. But before that, let's just ask, what is our estimate for the variance of error, right? Our estimate for this is going to be sigma hat squared, which we compute by finding the mean squared error that we talked about above, this SSR over 1 in the ANOVA table. And so there's a lot of notation, but I'm explaining all of the notation at once so that it kind of like comes together, and then you can look at this note sheet and follow along. Wait, sorry. This one is MSR. MSE is this one. And then, as we were saying, the SSE is the same as SYY minus SXX over n minus 2. Those could be easily found from the sum of squares and sums. And then after estimating the variance of error, we can look at the standard error of the estimated parameters beta 0 hat, beta 1 hat, right? Those are what we call the estimated parameters. Our standard error is basically the standard deviation, the square root of variance of the estimate. So SE beta 1 hat equals square root sigma hat squared divided by SXX. And you don't have to know why that's true, but look at the equation for beta 1 hat. That's pretty similar. This thing turns into sigma hat squared, and the denominator stays the same. So it's not too different. And SE beta 0 hat is going to be sigma hat squared times 1 over n plus x bar squared over SXX. And from that, we can find a confidence interval for beta 0, beta 1, right? So a confidence interval means we have the mean value plus or minus critical value times standard deviation, right? So in this case, it would be like beta hat I is between, or sorry, we're saying that the the true value of beta with some confidence is inside this interval. So 1 minus alpha confidence that beta I is within this interval. So the mean of the interval, the center of our interval is beta hat I, and then it's plus or minus our critical value, which we're using the t test. The t distribution. And so it's two-sided. So we have alpha over 2 and n minus 2. Up here is our degrees of freedom. And then our standard deviation is the SC of beta hat I. So like you can replace the I with 0 and 1. Substitute in these equations up here. We have a confidence interval fairly quickly. And then besides confidence interval for beta hat 1, beta hat 0, we can also do a hypothesis test for significance, right? So hypothesis test for significance of estimated parameters. So our null hypothesis is that beta hat, or just beta is 0, and our alternative is beta is not 0. So a significant parameter means under that confidence, it is non-zero. If we had 0 slope, then it's not really an intelligent linear model. If it has 0 intercepts, that's also not giving us information about the relationship between x and y, right? So this is an important test to see whether our linear model is giving us important information. And with these two hypotheses, like we can use the test statistic from that t alpha over 2 n minus 2 distribution, right? So our critical value is the same as above, t alpha over 2 n minus 2. Our test statistic is t0, which is beta hat I minus 0, which is the value we're testing against. We could test whether the slope is 5 and change it to 5 in both, right? But the important test is testing whether it's 0. And SE beta hat I is going to be our denominator, right? And so our rejection region is when the absolute value of t0 is greater than the critical value. We're doing a two-sided test. You could do a one-sided test and convert the rejection region. A hypothesis test for the betas, a confidence interval for the betas, and last thing we are going to talk about is a confidence interval for the y's. So first we'll talk about the confidence interval for the mean response at xi, and before we said that point estimate was expected value of y given x equals xi. We gave that the notation y hat I, right? And that was equal to beta 0 hat plus beta 1 hat times xi. After we choose the betas and an xi, then we know what y hat I is. Now we want a 1 minus alpha confidence and then an interval estimate. So we're saying that the value of yi is not a single point. Now it's inside this interval. It's going to be centered at yi plus or minus the critical value is the same, t alpha over 2 n minus 2. And then our standard deviation is a little different, but it's pretty similar to the interval for beta 0 hat. At beta 0, we have 1 over n x bar squared s xx. Here we have 1 over n x I minus x bar squared over sxx. And so that means at a specific xi, that changes our yi, and that changes the length of our confidence interval. And the length of the confidence interval is minimized at x bar. When xi is x bar, this comes out to 0, and we're just left with the 1 over n term in the parentheses. So our point estimate is that linear regression line like this, and then our interval estimate is changing lengths, right? So like this. At this point, x bar, we have the smallest length interval, and these should be the same, right? It's symmetric. But the length is not the same as it is over here. Over here, we have a larger estimate, a larger interval estimate, because we're further from the mean. And then the last thing I'd talk about is confidence interval for prediction is slightly different than mean response. Here we're also accounting for the error of the model, which was sigma hat squared, right? So we're going to add one sigma hat squared. So we're just adding a third term that is 1 inside those parentheses.